Let us start lecture 9, and the course is corrosion protection methods, and today's topic will be the remaining guidelines what we have to discuss for better design, and that can prevent corrosion to a great extent. So, the course is now we talked about total 6 guidelines, and there are few guidelines which will be covered in today's lecture. The point number 7, it says avoid hotspot. So, this is particularly important in heat exchanger, where during heat transfer process there could be a possibility of local increase in temperature, and that can also lead to several other problems like oxidation, local thermal fatigue, those kind of stuff can happen. So, this is important in case of heat exchanger. Where heat transfer happens from hot gas to cold gas or hot gas to cold liquid. Now, there, because of this local increase in temperature, which is the hot spot, there could be excessive oxidation, there could be thermal fatigue, there could be thinning down of the segment, that metallic segment of that pipeline, and then bulging. And finally, they could lead to a particular failure called fish mouth failure. So, if this is the pipeline, so there could be failure like this. Okay. There could be blast in that local spots, and that would lead to a catastrophic failure in the surrounding pipelines also. Now, one possible reason that we can discuss here. So, if you see the heat exchanger chamber, so let us say this is my chamber. So, this is refractory line chamber, and there will be a small hole through which hot gases are coming out, and if somebody wants to recover that heat, basically if we do not recover that heat from the hot gases, it will go to the atmosphere. This is happening in the secondary heat exchanger in chemical plant. So, if you recover that heat from the hot gases, you can make use of that particular heat for other preheating purpose. Now, in that chamber you have lined of tubes like this. So, those tubes are lined up and hot gases are going like this, and there will be exit. Hot gases, that cold gases are coming out, and these tubes, if you consider this a tube, This is the tube, and outside we have hot gas, and this is entry point. Mainly if we use steam, which is cold steam, and then when it goes out, exit point, it is hot steam, and this hot steam can be used for some other important purpose, and this is the flow of hot gases. Now, if we look at a small segment of it, let us say this is the segment we are talking about. If we look at the design of it, so that means, so this is the wall thickness of the tube, and this is the inner wall and outer wall, and through which steam is flowing. And by chance that hot steam is getting obstructed because of some eventualities there. So, that obstruction can lead to a turbulence there in the flowing steam, and also there could be a pressure drop. So, from this point to this point there could be a pressure drop, because this point we have sufficient pressure and this point is basically obstructing the steam flow. So, there will be definitely a pressure drop. Now, this steam is getting heated up locally. So, the local temperature around this zone will go up, temperature go up, and because of that, and steam can oxidize iron, and this particular pipes, let us say it is chromium containing iron, chromium containing steel, which actually gives a good amount of oxidation resistance. But if the temperature goes beyond the operation temperature range, then there could be excessive oxidation. So, that oxidation would lead to, let us say local oxidation is taking place, that could lead to decrease in the metallic component of the wall. See, outside is also getting oxidized, definitely. So, that means if you see this wall thickness, which is actually holding the load, that reduces, and high pressure zone is created here around this zone. So, that high pressure can give a huge amount of stress on top of this particular wall. And since we are actually reducing the wall thickness which holds the load, so there could be possibility of deformation of that wall. So, that is what the bulging happens. You can have a bulging like this, and here also bulging happens. Okay. At the same time, if that stress becomes critical beyond the fracture load of that thin segment of the wall, then there could be a blast as well as there could be a crack formation, and then crack will grow, and then there could be even that's what you have, this fish mouth failure. This is called fish mouth. So, this fish mouth failure, when it happens, there could be splinters, and that splinters can hit the side pipes also, and like that way there could be a failure from one end to the another end. And once there is a failure, of course, your heat transfer process will be hindered, and in fact, sometimes the blast can be so severe, it can also hit the walls of that chamber, and there could be damage to the refractory lining. So, that time, in fact, you have to stop that operation, and there could be repair. So, good amount of time will be spent as well as money. So, that is what these local hotspots are dangerous from the point of effective heat transfer operation. So, and this is related to excessive oxidation, thermal fatigue. Thermal fatigue means, for example, this particular segment is having high temperature, temperature is high, let us say close to that segment the temperature is low, and there could be local expansion, and that local expansion can lead to a thermal fatigue. Okay. So, that can also lead to a failure, and of course, the bulging can happen because the steam movement is hindered because of some reason, and the one reason could be if excessive oxidation happens. So, this oxide can fall off and then deposit at the bottom. So, this is the oxide deposit, and those deposit will reduce the orifice dimension. Okay. So, the total pathways for the steam flow will be low, and that would again lead to a pressure drop. So, that means this end will be having high pressure, this end will be having low pressure because of the steam not flowing properly. That would lead to all those subsequent processes, and finally, we have fish mouth failure in the heat exchanger. Okay. So, this is one problem which can happen. Even hotspots can lead to stress corrosion cracking. Okay. So, that is also possible. Stress corrosion cracking due to hotspots. So, we have to avoid hotspots. That means, all the time we should maintain the flow. We should, in case if it is needed, we need to have a better materials which can have a better oxidation resistance, as well as proper parameter control, like the hot gases temperature should be within a range, it should not go up. The steam flow rate should be always maintained. In case we see that there is a pressure drop, we should have a little extra pressure from inlet, so that that debris can just go out. Okay. So, those possibilities are there. That means, process control should be properly monitored, otherwise this fish mouth failure can happen. Now, 8th point, we should design to exclude air. One example we have already cited, that electronic items, when it is packed, it is sealed properly, so that no more air can go in. It sometimes we actually do a little bit of evacuation, so that air goes out, and when air goes out, you are actually removing oxygen. So, what you are doing, oxygen you are taking out, and oxygen is a serious oxidant, and it can participate in the presence of moisture, this cathodic reaction, and this is a strong cathodic reaction. So, once there is a strong cathodic reaction, and if there is moisture, then definitely the metallic component, let us say iron, can go into a corrosion mode. Okay. So, the corrosion of iron can happen. Okay. So, if you take care of it, you remove air. So, you are reducing the partial pressure of oxygen, you can avoid corrosion factor or corrosion effect. Now, sometimes in some metals like titanium or stainless steel, in case of stainless steel or titanium, presence of oxygen can be helpful. So, the character of this particular titanium and stainless steel, so they are passivating metal. And actually, in oxygen presence and H2O, or rather I would say active passive metal. So, that case oxidant can help to achieve passivity. So, we have discussed this in greater details in our previous lecture series. So, we can just quickly discuss that. See, if we talk about E versus log I plot, which is coming from mixed potential theory. So, this is my this is the typical behavior of the metal if it shows active passive behavior. Now, let us say the cathodic reaction is here, fine. This is the cathodic reaction. And this is basically coming from anodic polarization. Which is metal, let us say stainless steel, iron or chromium mainly. So, there if we consider iron 2E equal to Fe plus plus, iron can also show active passive behavior. Now, generalized, if we can put it in a generalized fashion, let us say M minus Ne equal to Mn plus, and this cathodic reaction, let us say oxygen reduction. Okay. So, that time, so this is also showing anodic cathodic polarization. Now, that time this is my I core. If the cathodic polarization line cuts the active passive metal in the active zone. But if we add oxygen, adding extra, so that means partial pressure of oxygen goes up. So, this point can go up here. So, this point can go to this, because higher the partial pressure of oxygen, higher would be the potential or the equilibrium potential. So, the equilibrium potential would change and then it can cut here. So, this is the second level of polarization after having higher partial pressure of oxygen. So, that polarization happens, it actually cuts the active passive metal in the active zone, and then my corrosion current density would be I core here. So, let us say this is second, this is 1. This is case 1, this is case 2. Now, you could see that since this is in log scale, so that means once you have oxidant presence or partial pressure of oxygen, if it increases, so then equilibrium potential would go up, because my equilibrium potential can be given as so this is this is 4 OH minus. Okay. Now, this is if you fix the temperature as well as pressure, this is fixed, all those parameters are fixed. So, if you, so this is let us say pure, so it can be considered as 1. If you fix OH minus ion concentration, that is also fixed. So, if you increase this, definitely this value goes up. So, that is what there is a potential increase or the equilibrium potential increase. So, this is the effective this is the equilibrium potential, this is the equilibrium potential, fine. And you are seeing that the passivation is achieved. So, the material would corrode according to this current density. Lower the current density, lower would be the corrosion rate. And if you do polarization behavior, you will see the typical polarization behavior in the first case, and here another information is I core second case, which is a passive range, passive, it's much less than I core type 1 or the case 1, which is active. So, this way you can actually improve the corrosion resistance of those materials which are active passive behavior. But otherwise, in case of active material, definitely if we reduce the oxygen partial pressure or if you exclude air, it will reduce the corrosion rate. So, that can also be explained. So, if you consider active metal, again E versus log I plot you can do. So, this is my active metal, it does not show any active passive behavior, and let us say this is the cathodic polarization line, and this is the anodic polarization line, metal dissolution. So, this is my corrosion rate I cor 1, where partial pressure oxygen is high. But if you reduce it, this potential would go down and it can come here, okay, and you will have another polarization. So, now you see, because of the reduction of partial pressure, so this would be my I cor 2 when PO2 is less. So, I cor 2 PO2 less is less than I cor 1 PO2 high. So, this is the explanation, and I was talking about the polarization plot. If you are interested, you will see the polarization plot for this, it would be like this, and the second case it would be like this, and here it would be first case would be it will be like this, and the second case would be like this. So, this will be the pattern of polarization behavior, right. So, now excluding air would be helpful in case of active metal, but excluding having little air or oxygen can be helpful for active passive metal. Now, ninth point is any sort of heterogeneity, that should be avoided. Like if we consider inhomogeneous alloy, a component with inhomogeneity, composition and inhomogeneity, that can have pitting susceptibility. All those, if you see this particular plate, those inhomogeneous points can lead to pitting, and if there is tensile component, it can lead to stress corrosion cracking. Or SCC. Now, we have already talked about stress inhomogeneity. We have talked about galvanic inhomogeneity. We had talked about heat inhomogeneity. Okay. In fact, we can also talk about oxygen partial pressure inhomogeneity. At times what happens, let us see some section, if that section gets a less amount of oxygen, you are going to create high degree of concentration cell. So, the low oxygen place can have higher anodic tendency, and this is related to concentration cell. So, this is a typical, for example, if some places we are seeing crevice, if there is accessibility of sending air, If we send air, actually crevice corrosion can be prevented to a great extent. What we are doing, we are actually avoiding or replenishing oxygen there. The crevice, when crevice attack happens, one of the initial start point is the depletion of oxygen from the crevice point. And once depletion of oxygen happens in the crevice point, for example, if you have a crevice like this, okay, so this is let us say crevice. In the beginning, everywhere you will have equal amount of oxygen reduction, but if it is a stagnant solid, okay, and that stagnant if it is a stagnant liquid, let us say stagnant NaCl solution, then this particular part, this particular segment will have less oxygen after some time, because whatever oxygen was there in the beginning, those actually got consumed because of cathodic reaction. So, this is stagnant. The condition we have to also mention, the stagnant NaCl solution. Okay. So, when we have that, initially everywhere same oxygen, but as the reaction is going on, oxygen will be depleted in the crevice portion, less oxygen. So, this particular away from crevice, high oxygen, and if we consider these 2 points, this will be anode, this would be cathode. As we have seen in the previous case, if we have high oxygen, if we take this reaction, let us say this particular Nernst equation, high oxygen means this particular potential would be high, low oxygen means this potential would be low. So, this will have a low potential and this will be having high potential. What happens? Other places we have sufficient oxygen. So, in order to meet the requirement of electron for this oxygen reduction, again the oxygen reduction is same as in neutral solution. Iron would dissolve here and there will be a dip or a sharp inward corrosion of iron, and so this is typically the crevice formation, and of course, the chlorine ion will also take part in the process. In the first class we talked about that chlorine ion effect. Now, if we actually star this particular solution, if we star this particular solution, the stagnancy would be out and then this is exposed to the open air. Oxygen containing air will go to this particular crevice portion, and once oxygen goes there, so everywhere you have similar level of oxygen, crevice can be stopped. Okay. So, that is the purpose of writing this. Oxygen partial pressure inhomogeneity we should not have, which can lead to crevice actually. Okay. So, crevice can be avoided if we have similar oxygen partial pressure in the liquid, even in the crevice zone. So, this is about removal of heterogeneity. We have talked about galvanic, we have talked about heat heterogeneity, inhomogeneity, stress inhomogeneity, and we will talk more on those kind of things by giving several such design examples. And the 10th, so 10th is about site location. Okay. The site location, or we can say that place to install. Okay. Whether it is a plant or whether it is warehouse or whether it is a kind of a design of equipment, we should take care that if there is air flow, and whenever air flow happens, there could be possibility of this particulate matter that is also coming along with the air. Sometimes that air flow can take the hot gases coming out from chimney, and that can hit the another chimney if the height of those two chimneys are different. For one typical example, let us say we are designing a chimney. So, this is one chimney and hot gases is coming out and air flow is this direction. Now, if another chimney is designed very close to that with a higher height, so this is coming out. So, these particular chimneys, the gases which are coming out, those are hot gases along with several suspended particles. So, those particles are heating here, and this particular part of the chimney, can go into a severe corrosion process or erosion corrosion, all those effects can be felt there. So, the better design would be, if see airflow we cannot change. So, only thing we can change is, instead of making different height, we can make them same height. So, airflow is going like this. So, the minimum interaction of those airflow coming with the gases which are coming out from the chimney, there is a minimum interaction of that gases with the other chimney. So, this is the better design, and this is a bad design. So, this is one such example. Similarly, let us say a sea site, okay, and airflow. So, if there is airflow as well as something is close to the sea site, we should not keep storing materials or instruments which are getting access to the sea water. That means, when sea site is there, the air, and if it is a strong airflow, then the airflow can actually take some of the small droplets, seawater droplets along with it, and that can deposit onto those materials. So, for example, if there is a sea site and airflow is this, and if we are having a room like this, let us say, okay. So, now if you try to store something here, okay, now definitely this particular region can have lot of salt water deposit, and definitely those can go into a severe atmospheric corrosion. So, the site location is basically to avoid atmospheric corrosion. Of course, or erosion corrosion. So, those kind of corrosion aspect can be avoided. Now, if we see that we have talked about around 10 guidelines, and these 10 guidelines were taken from the book by Fontana and Green. There is a book named Corrosion Engineering. At the same time, I have taken help from another book which is written by Professor U.K. Chatterjee, Professor S.K. Bose and Professor S.K. Roy. Those are former professors in the Department of Metallurgical and Materials Engineering, IIT Kharagpur. So, they have written a book on corrosion. So, I have taken some part from that particular book also, and of course, there is one more source material which is basically ASM Handbook volume 13A. So, if you follow those books, definitely you will get to this particular part more better, I would say better understanding will be developed. But if you see in a short, that these are the some guidelines which can prevent corrosion to a great extent, and those guidelines are based on the design criteria. Okay. So, let me close here, but in the next class onwards, I will show some typical photographic evidence of better design. So, till then, thank you.